Everybody, my name is Rebecca Hounsell. I'm going to be the session chair for Cosmology 3. It is my great pleasure today to introduce you to our next speaker, and I apologize if I pronounced your name incorrectly. It is Hahn from Princeton University, and they will be discussing extracting the full cosmological information of Roman with SimBig. Thank you very much.
Thank you so much for having me. My name is Hahn. You can call me Chang. I'm a postdoc at Princeton. So today I wanted to tell you about some of my recent work, which I think will be helpful in one of the ways that we can really extract the full cosmological information from Roman. But before I begin, I know it's a pretty diverse crowd, so I wanted to give a very, very brief introduction. So at this point in cosmology, we've really converged onto a standard model that we call lambda CDM. And according to this model, the universe started with the Big Bang. It then entered a period of accelerated exponential expansion that we call inflation that seeded the initial density fluctuations in the primordial plasma. Then after the photons decoupled from the primordial plasma to what we observe as the cosmic microwave background, or CMB, the baryonic and dark matter in the universe, they gravitationally form the stars, the galaxies, and the larger structures in the universe. Then around 10 billion years, the universe entered a period of accelerated expansion driven by dark energy. So in addition to providing this nice history of the universe, the primary reason why we've converged onto the lambda CDM model is that it's been remarkably successful at describing current observations. So this is one example of this. This is the temperature power spectrum of the CMB from the Planck satellite. The blue points are measurements from Planck. Meanwhile, the orange lines are the predictions from lambda CDM. And as you can see, the predictions really go through almost nearly all of these data points with remarkable accuracy. But despite the successes of lambda CDM, one of the challenges is that none of the main ingredients of components of lambda CDM are well understood. And recently, we've entered this really exciting time in cosmology where there's been cosmic tensions between measurements of from the early universe versus the late universe. So let me expand on that a little bit. Right now, I'm showing you measurements of the growth of structure from CMB experiments that probe the early universe at high redshift. And so compared to these measurements of this S8 parameter, experiments that probe the late universe at low redshifts with weak lensing, we find significantly lower values of S8 compared to the CMB experiments. In addition to this S8 tension, we also have a tension in the present-day expansion rate, parameterized using this H0 parameter, the Hubble tension. And I'm again showing you measurements of H0 from the CMB experiments that probe the early universe at high redshift. And again, compared to these measurements, what we find in experiments that probe the late universe at low redshifts are significantly higher values of H0. So over time, as our experiments have gone more and more precise, the significance of these tensions have only increased over time. So one way we can address both the S8 and H0 tension is with spectroscopic galaxy surveys that allow us to probe both the growth of structure and the expansion rate of the universe. So spectroscopic galaxy surveys, they provide the photometry, and they also provide spectra of galaxies that then allow us to produce detailed three-dimensional spatial distributions of galaxies like the one I'm showing you in the background here from SDSS. And aside from creating these beautiful maps, it also contains a tremendous amount of cosmological information. For instance, it encodes information on redshift space distortions that allow us to probe growth of structure. So the redshifts we measure of galaxies, it has two components. It has the redshift from the cosmological expansion and also the redshift from contribution from the peculiar velocity. So a galaxy distribution, which would look like this in real space, would be distorted in redshift space to look like this. And there's two regimes of these redshift space distortions. There's the very obvious fingers of God, which are these long elongated structures that point towards the observer due to the random virialized motions of random motions of galaxies in virialized structures. And there's also the more subtle effect, which you might notice if you look at the more overdense regions here. You'll notice this squashing along the line of sight. And this is the Kaiser effect caused by the coherent motions of galaxies towards large-scale structure. So as you can imagine, this effect encodes information about the growth of structure. So we can write down the overdensity of galaxies in redshift space in terms of the overdensity of galaxies in real space, plus this term that determines on the growth rate of structure and the matter overdensity. And in practice, we use a summary statistics of this overdensity, such as the galaxy power spectrum, and we're able to measure the growth of structure that way. So this is measurements of the power spectrum at 2 redshifts from SDSS. And so by making these power spectrum measurements, we can then probe the growth history of the universe. So in addition to the growth of structure, we can also probe the expansion history of the universe using baryon acoustic oscillations. So in the early universe, as I mentioned, the baryons and the photons are coupled and they propagate as spherical sound waves. Then when the photons decouple from this plasma to the CMB, the baryon acoustic oscillations are frozen in place. So what that means is on the scales of this baryon acoustic oscillations, BAO, galaxies are more likely to form. So if we were to measure their 2-point correlation function, we would find a slight increase in the probability of finding galaxy pairs at the physical scale of the baryon acoustic oscillations. And then we can use that as a standard ruler to then measure the expansion history over time. So hopefully this is a brief, very, very brief crash course into how we can extract information on both the growth and expansion history of the universe from the 3D galaxy distribution and the current standard analyses that we use for these analyses. However, the current analyses, they only exploit a small fraction of the actual total cosmological information in galaxy surveys. And that's because they primarily focus on using the power spectrum and also on large linear scales. So this is, again, the measurement of the power spectrum that I showed earlier. And you can see a vertical dashed line where I've marked the current scale cuts used by analyses. So these scale cuts, which correspond to a Kmax value of 0.2, is primarily because we use analytic models of galaxy to model the galaxy power spectrum that's only accurate in the linear regime. However, there's obviously more information available on smaller scales, and also there's more information available beyond the power spectrum. So this is a nice illustration that I always like to show. This is by Emiliano Sefusati. Here are 2 distributions that by eye are completely different from each other. But if you were to look at their power spectrum, you'd find that they're nearly identical. Of course, if you look at any higher order clustering statistics, like the 3-point or the 4-point, which I'm sure was mentioned earlier, you would immediately notice significant differences between the 2 distributions. So the question still remains, how much cosmological information is available beyond the power spectrum? So a couple of years ago, to answer this question, I, with collaborators, constructed these 2 suites of simulations, the Quixote and the Molino suite, which are tens of thousands of simulations built on top of M-body sims in order to quantify the information content of the cosmological observables beyond the power spectrum. So based on these forecasts that we conducted with these simulations, what we found is, and in this figure, I'm showing you the forecast for the power spectrum in blue and the power spectrum plus the bispectrum in orange. And we can see that we, with the bispectrum, we can constrain lambda CDM parameters with more than 3 times the precision of the power spectrum alone. We also find that there's significant information beyond the current scale cuts. So this is a rather busy plot, but I'm showing you here the 1 sigma value of the forecast as a function of the Kmax scale used. And in each of these panels, I've labeled the current scale cuts. And you can see that as we go down to larger and larger Kmax or smaller scales, we are able to improve all of the lambda CDM parameters pretty significantly. And at this point, we've done this for multiple different clustering statistics beyond the power spectrum and find consistent improvements over the power spectrum alone. So clearly there's significant amounts of higher order and nonlinear cosmological information. But if we try to take the current approaches for analyzing the power spectrum and extend it to these, we immediately run into a number of challenges. The first challenge is that, as I mentioned earlier, we use analytic models based on perturbation theory. And these models are inaccurate on nonlinear scales, especially for higher order clustering. So this is a plot from Chudakin and Ivanov, where the blue error bars are showing you the uncertainty of the bispectrum. And on small scales, these uncertainties come from the theoretical uncertainties. So you can see at beyond K max of 0.2, you're completely dominated by your theoretical uncertainties. So you wouldn't be able to extract any cosmological information from those scales. And of course, there's currently no analytic model that's available for many of the summary statistics that people have found to be very promising, like wavelet statistics, kth nearest neighbor, or minimum spanning tree. So there'd be no way to analyze these with the standard perturbative approaches. So in addition to this, the other challenge we face is that observations in reality are quite messy. This is showing you the angular footprint of the Boss CMAS sample, and you can see all of these imprints of masking and photometric systematics, and all of these have to be taken into account. And these can play a very, very major role in affecting your clustering measurement. For instance, fiber collisions can strongly affect small scale clustering, as I'm showing you in this figure, where we estimate the effect with 3 different simulations. And you can see even at Kmax or K of 0.1, the effect of fiber collisions is larger than cosmic variance. And at the moment, there's no correction scheme that's available for higher order statistics for effects like these. So here's what I think are the current challenges in terms of actually extracting the information in higher order clustering and on nonlinear scales. But of course, this is only if we try to extend the current approach to analyzing galaxy clustering. But if we instead use a simulation-based approach, we can actually tackle each of these challenges. So in terms of modeling the nonlinear scales, well, while we are limited with perturbative approaches, if we instead used M-body simulations, we can accurately model down to much, much smaller scales. In terms of clustering statistics beyond the power spectrum, if we use a simulation-based approach, we can use any statistics that we can measure in the observations, as long as we consistently measure them in the simulations themselves. And lastly, in terms of the observational systematics, we already have a lot of the tools to forward model many of the systematics that we face with galaxy surveys today. So the only challenge that remains with the simulation-based approach is how do we go from a simulation like this that includes, that can accurately model small nonlinear scales that include all of the observational systematics to the cosmological parameters that we're ultimately interested in. In other words, how do we derive the posterior of the lambda CDM parameters given the galaxy distribution? And so the way we can tackle this is by using simulation-based inference. So briefly, to give a primer on what simulation-based inference is it's a way of doing Bayesian inference where the only assumption we make is that we have some stochastic forward model or simulator that takes in some input parameters, in our case, the lambda CDM parameters, and is able to produce the observable that we're interested in. And if we have just this forward model or simulator, we can, one of the things we can do is we can pick some theta prime here, run our forward model, generate a sample, generate a couple more, and we can keep repeating this process. And then this distribution that you get with all of these simulations is actually the likelihood. So really, if you have this forward model or simulator, this implicitly defines our likelihood. And so simulation-based inference takes advantage of this. So one of the things you can do with a forward model is first sample the prior that you're interested in for your parameters, and then afterwards run the forward model for each of these theta values that you draw. So for instance, repeating this process until you have a full sample of these theta and x points. And then this distribution is actually just the joint distribution of the observables x and your parameters theta. And so if you have some actual observation x obs here, one of the things you can do is simply remove all of the data points that produce x values that are significantly different than the observation you just made, and then just look at the distribution of the leftover simulations, and that is that approximates the posterior that you're ultimately interested in. So the process that I just described, this very simple process, is actually one of the simplest versions of simulation-based inference called approximate Bayesian computation. Now, of course, in practice, this process of throwing out most of the simulations that you've generated is actually pretty infeasible. So instead, what you could do is reformulate the inference procedure as a density estimation problem. So can we estimate the posterior of theta given x from a number of simulations, which is equivalent to a number of draws from your likelihood. So we can here's the problem that we're facing, which is to estimate the posterior given a number of samples drawn from the joint distribution of x and theta. So Q of phi here is some model with free parameters phi. And so one way we can determine the phi that gives us as close of an approximation to the posterior is by minimizing the callback labeler divergence between these two distributions that I've written here. The KL divergence is also known as the relative entropy, but you can think of this as sort of a distance metric measure between two probability distributions. So a large value of the KL divergence would mean the two distributions are very different. A value of 0 means that they're identical. So the nice thing about the KL divergence is here's the equation for it, but you can rewrite it in rewrite this. This expression here is P of X, the joint distribution here. So then we can approximate this with a Monte Carlo integration using the samples drawn from the joint distribution. And so we can rewrite this whole expression, since this top part does not depend on phi, as just minimizing of the negative log value of Q, or maximizing the log Q evaluated over all of the samples of your forward model. Now, in the case where Q of phi is flexibly expressive, meaning is flexible enough to actually approximate P, and in the limit of infinite samples and successful optimization, Q of phi is guaranteed to converge into to the true posterior. Now, in order to make the first and the third criteria possible, the model that I like to often use is normalizing flows. And briefly, without going into any detail, they're a bijective transformation that goes from a Gaussian distribution to the target distribution that you're interested in with a series of transformations that are both invertible and differentiable, which means that you can use change of variables to evaluate the target distribution by evaluating and sampling a simple Gaussian distribution that you're interested in. And the other advantage of normalizing flows is that each of these transformations are described by a neural network, and you can combine many of these in order to make it more flexible and descriptive. So without going into any more details, here's some examples of normalizing flows describing airplanes, chairs, and cars. And these are estimating the probability distribution of planes, chairs, and cars. So going back to what we're actually interested in doing, which is this inferring this posterior from simulations. To do this, I've been working and leading the SimBig collaboration, which stands for the Simulation-Based Inference of Galaxies. And so our framework starts by first generating training data of synthetic observations. So starting from the cosmological parameters, generating synthetic galaxy surveys, and then compressing them into the summary statistics. We then take this training data set to train a normalizing flow. And then after we train this flow, we repeat the same data compression to the summary statistics for the actual observations. We plug it into the trained normalizing flow, and that gives us the posterior. So most of this is just standard SBI. So I want to talk a little bit more about the first step, which is how we generate the synthetic galaxy surveys. So our target observations is the SDSS3 BOSS sample. So we start with the Quixote high-resolution M-body simulations. We identify the halos in the simulation using the Rockstar phase space halo finder. And then afterwards, we populate these halos with galaxies using an HOD model with assembly bias, velocity bias, and concentration bias. Then afterwards, we apply all the survey realism of the SDSS sample. So we put it into redshift space, we apply the geometry, the masks, and the fiber collisions. So in total, we construct 20,000 training simulations that span a broad range of cosmologies and HOD parameters. And here's one example of how our forward model simulations on the right compares to the actual observations on the left. The color here represents redshift, and I want to focus on just all of the details and the observational systematics that we include in the forward model. And again, this is essential in order to account for all of the effects of systematics. So now that you know how the SYMBIC framework works, we can apply this to actual clustering statistics. So the first statistic we applied this to was the galaxy power spectrum. But since we use a simulation-based approach, we go down to significantly smaller scales to Kmax of 0.5 rather than the standard Kmax of 0.2. So here's what the full posterior looks like. The top set of contours represent the posteriors for the lambda CDM parameters, and the bottom set here are for the HOD parameters and nuisance parameters. So focusing on omega matter and sigma 8, here's how the SYMBIC constraints in blue from the power spectrum compares to the standard power spectrum analysis using effective field theory from Misha Ivanov in orange. So because we're able to extract information from nonlinear scales, we're able to improve our constraints in sigma 8 by a factor of 1.4. Now, of course, this is still just using 2-point statistics. So the next summary statistic we applied this to was the nonlinear galaxy bispectrum. So here's how our constraints in black for the bispectrum compare to the constraints from the standard power spectrum analysis. So in this case, we're able to improve both omega matter and sigma 8 significantly over the power spectrum analysis. And again, this is from extracting information in higher order clustering and also on nonlinear scales. So in addition to the bispectrum, we also tried another summary statistic, which was a convolutional neural network summary of the galaxy field. So you can think of this as an attempt to extract all of the relevant cosmological information in not just the 2-point and the 3-point, but all of the endpoint functions. And when we apply SYMBIC to this, we find consistent improvements from the bispectrum in improving both sigma 8 and omega matter. So at this point, we've applied this SYMBIC to wavelet scattering transforms, to skew spectra, to the Mark power spectrum, and we're also working on applying it to voids, graph neural networks, and a combined analysis, which we'll produce soon. So going back to the original constraints that I started the talk with, sigma S8 and H0, here's how the SYMBIC constraints compare to the standard power spectrum analysis in the black dashed line. So you can see that we're able to improve S8 by almost a factor of 2 and H0 by more than 50%. So one thing I want to emphasize here is that this is not a proof of concept applied to idealized data or simulations. This is actually applied to observations. So these are real production level constraints. And for the non-cosmologists out there who might not know what a factor of 2 is equivalent to, this is roughly equivalent to analyzing a survey with 4 times larger volume with the standard power spectrum analysis. So this is a really significant improvement over the standard analysis. Now, of course, everything that I've talked about is still with just hundreds of thousands of galaxies at around redshift of 0.5. But fortunately, we have many surveys on the horizon, and I guess in this case, also the Roman Space Telescope here. And these will provide really very exciting samples of millions of galaxies spanning the redshifts of 1 all the way up to redshifts of 3. And so going back to the figure that I showed with the S8 and H0 tension in the very beginning, over the next few years with the current ongoing galaxy surveys, we'll have constraints with SYMBIC on both of S8 and H0 parameters all the way out to redshift of 1.6. Then with Roman, we'll be able to really fill this gap between the early and late universe at higher redshifts. And with SYMBIC, we'll be able to extract even more information than the standard analyses that we for galaxy clustering. And this really will allow us to test new physics beyond lambda CDM all across cosmic history. So I want to end here. That's all the time I have. And just summarize that galaxy surveys really encode tremendous amount of cosmological information in both the growth and expansion histories of the universe. Um, I think SIMBIG is one of the new approaches that leverage machine learning to really extract all of the information that's available in nonlinear and higher order clustering. And in the case of SDSS, we demonstrated that we can really double the cosmological impact of galaxy surveys by doing so. And I think it is a really exciting time for galaxy clustering in general, with not just the current ongoing surveys, but also with Roman on the horizon, which will really allow us to measure these cosmological parameters all across cosmic history and enable us to probe new physics in the coming years. Thank you.
Thank you very much. Do we have any questions from the audience or even members online?
Hey Cheng, really great talk. Zach here, so a fellow three-point function bispectrum enthusiast. I wondered, you said you have about 100,000 galaxies from CMAS. Is that because you did a small kind of subset of CMAS because the simulations weren't, able to be big enough to cover it? And I guess if that's true, how are you thinking about doing this for all of DESI? How can we get enough simulations that cover the full volume to enable this inference?
That's an excellent question. So in the case of SIMBIG, we used the Southern Galactic Cap of CMAS. So that's why it's hundreds of thousands of galaxies. Um, Trying to do a naive extension of SIMBIG with just bigger simulations is challenging, mainly because you have to go both bigger volume and higher resolution at the same time to get some of the H alpha emitters and the emission line galaxies. So the approach that we're working on now for SIMBIG 2 or SIMBIGger is the hybrid simulation-based inference approach that was introduced by Chirag Modi and Oliver Philcox, where you you split the likelihood into the likelihood from the large scales and the likelihood from the small scales. And for the large scales, you use a perturbative approach. And for the small scales, you would use simulations. Another approach that we're exploring is also, instead of running full simulations at the larger volumes and the higher resolution, is to use emulation approaches that have now been demonstrated to be effective at accurately reproducing small scale. So you would train lower resolution, cheaper simulations, run it through an emulator, and then that will output an emulated version of the high resolution large volume boxes.
Thank you very much. We have another question in the audience.
Hello, this is Eric Huff. As I'm sure you know, one of the big problems that we've been worrying about with more recent survey measurements is unknown systematics. And I'm wondering, with the modeling flexibility that you've implemented here, if you've thought much about how to self-calibrate clustering or lensing systematics with SIMBIG or a similar framework.
So we haven't implemented any self-calibration yet, but I do think that is one advantage of a simulation-based approach that we have thought about but haven't explored yet. So if you have any and I'm mainly used to ground-based galaxy surveys, let's say imaging systematics that you don't fully understand, whether it's from dust or just variations in the image quality. I think some of those you can actually quantify with nuisance parameters into the forward model. And since those are relatively cheap to simulate, you can generate many, many realizations and effectively marginalize over some of these systematic effects. So I think that's one way you can tackle some of these quote unquote unknown unknowns.
Okay, thank you very much. Any other questions from the audience?
Hi, Cheng. It's David Weinberg. Beautiful talk and work. My question is sort of related to Eric's, I think, in that something I like about the traditional, summary statistics straight up comparison thing is these, when the parameter constraints get interesting when they give you something surprising, right? When you find W is minus 1.2 or the neutrino mass is negative or something. And then you can, in the usual approach, you can say, well, let me force that parameter to be what I think is a reasonable value, and then look and see where things disagree. And sometimes that gives you clues to the physics. Sometimes that gives you clues on the systematics, like the dark energy survey, high redshift clustering would be one example of a systematic that just kind of turned up by seeing, well, what actually disagrees if we impose a model we're more inclined to believe. So my question is do you see a kind of comparable systematic way to do this within simulation-based inference, which at the moment still feels to me a little more like a black box, so where you find something surprising, it's harder to put your finger on what's causing it?
So that's an excellent question. I think you can, with simulation-based inference, you could in principle take the same approach of, especially if you do neural likelihood estimation, of taking the parameter forcing some parameter and then looking at what the summary statistic predicted by is. And I think already we've already found some interesting things where one of the lessons that we learned from SimBig is that it's relatively easy to break the simulations, or actually break the clustering analyses if we push it the limits of the summary statistics. So this is showing you the S8 and H0 constraints that are from the wavelet scattering transform and the convolutional neural network compression of the galaxy field. And you can see they're much, much smaller constraints than the results that I showed you. So for instance, one of the tests that we do, and the test that these two contours didn't pass, is we ran them through different test simulations generated using different forward models. And you can see in this last panel here that there's differences in the likelihood that's predicted by them. So already this suggests that there's some deviations from the model that the wavelet scattering transform picks up that the power spectrum isn't able to pick up. So we're still in the process of sort of teasing out what the problems are of the model are. But I think this is one way we can go forward in terms of learning new things about where, let's say, our lambda CDM model is limited and things like that.
Thank you very much. Let's thank our speaker again.